Hello, friends. Well, it's time to think outside the box. The last couple of years, I've been pursuing this project. I haven't made much of a dent, but I'm right. Okay. Um, I had 8 years of very intense science and math classes, university classes. They're the hardest ones I could find. And well, just as an example, this is my last calculus test. And my last calculus class, the notes from that class, I guess you can't see them very well, but there's hundreds and hundreds of the most advanced calculus problems here that you can solve, and I got them all right. But this is just one class, one semester, and I did this for 8 years, 16 hours a day. So is there any possibility I would get all those problems right and scratch on this one? No, there is no possibility. So how do you make a dent in this Einsteinian mass delusion? I guess you could call it. It's not easy. But while I was waiting around, I thought I'd try my hand at this starlight deflection problem that garnered Einstein a ticker tape parade in New York in 1919. A ticker tape parade because he predicted the deflection of starlight coming past the sun as confirmed by a fellow by the name of Eddington. In 1919, he validated Einstein's prediction. But all this was fraud and all it was staged. And, I tried to say these things not long ago. I put this paper where I solved this problem out on a physics site, and I got dozens and dozens of hate emails, all kinds of names, and no more than that. I got phone calls, international phone calls all night long, which thank God I didn't bother to answer any of them because I'm sure it would have been fun. So here we are again, and I tackled this problem, and it turned out a lot better than I thought because there's no guarantee that I'd be able to solve it, and I really hardly understood what they were talking about. So let's just get to it, okay, and try to keep up. If you don't have a degree in hard science, you probably don't want to try it. And if you do, and you're not too brainwashed, and you really are good, you'll see that I'm right. But it seems like over the last 110 years or 100 years or so, that I alone, at least as far as I know, no one to actually take a hard look at this stuff and give you a correct answer. Now, before the James Webb telescope was put up, I wrote and I said, and I can prove it, that it would prove there was no Big Bang, because you don't need the James Webb telescope to prove there's no Big Bang. But they've been telling us this for 100 years. And in the last decade or few decades, they've come up with this cosmic microwave background, which absolutely proves it. Hundreds and thousands of videos talking about the Big Bang, the Big Bang, the Big Bang, when there could not have possibly been a Big Bang. And I said, okay, so is it possible, now that the James Webb telescope has proved that there is no Big Bang, is there maybe something wrong? Is it possible that I'm right? Well, wait a minute. I was right. Is it possible they're wrong about everything? Yeah, they're wrong about everything. Einstein was a fake. So, hang on. So now I am sure that you won't be able to follow the proof of the starlight, correct proof of the starlight deflection as I will present it, unless you have a firm grasp of the Pound-Rebka experiment and what it tells us about the movement of light and the action of gravity. So the facts of the Pound-Rebka experiment we will discuss now. And I have this page here that this actually is taken from the wiki article on the Pound-Rebka experiment. You can Google it up yourself and see that what I'm telling you is right. And if you got a head on your shoulders, you'll be able to see that I'm right. So what we have here on the top, it's got a slightly gray background. This Pound-Rebka experiment, the point of it was to prove Einstein's contention or validation of his relativity that clock speeds are slower the closer you get to the Earth. So what you do is you drop an object to a certain distance h, and you measure the change in frequency, is the idea. And since the definition of a meter is based on clock speed, if the clock speed decreases, then the length of a meter decreases. Well, if the frequency increases, the wavelength decreases from this height, as you drop it down to this height over this change in elevation, that there will be a fractional change in potential energy, and that fractional change in potential energy will be equal to a reduction in wavelength that we verified with this experiment. And if the wavelength of light is reduced, then the clock speed must be reduced. But they tell you that. They say this, we're going to prove relativity. And this is as far as they go right here. This is proof of relativity. Now see this formula here for the change in frequency. We've got the end frequency is equal to the beginning frequency times this very complex equation, complex expression. Can you see how that works? See, this is my example of a fake. Well, wait a minute, though. Maybe I'm just not smart enough to get it. Well, apparently the authors of the Rookie article weren't either, because they say, okay, now that we've proved Einstein's formula, we're going to throw it out because the value of h in this formula is insignificant. Well, that was the whole point of the experiment, wasn't it? The change in frequency or length or clock speed over this distance, fractional change in potential energy. The fractional change in potential energy is going to reduce the frequency or increase the frequency and reduce the wavelength by the same amount, by the same fractional amount. That's what this equation is supposed to tell you. But obviously, what's the point of trying to figure out whether or not it gives you the right answer? Now, you can do that, but it's not that easy, and who cares? Because they take and throw it out, because that's not the point of it. And then they give you this little equation here. And this says the instantaneous change in energy divided by the original energy is equal to, well, this is actually the formula for potential energy, isn't it? So it's potential energy divided by c squared. It's actually potential energy includes mass. All this is the change in velocity. GH is the change in velocity. G is the rate of falling bodies over the height h, and that will give you the change in velocity over the distance h. And you can take that and divide it by c squared. Well, that's the change in velocity squared. And if you divide that by the velocity of light squared, you can remove the square from top and bottom, and you end up with just the fractional change in velocity over the distance h. They don't explain this stuff very well, and I'm telling you, not many people will really get it. You have to be able to understand this. You have to be able to get this, digest it. Okay, because they're not going to explain it very well. And besides, we already knew that, didn't we? The change in energy, the change in potential energy over the distance h. That's Newton's formula for potential energy. This is no brainer. That isn't what we wanted. What we wanted was the change in clock speed. And obviously, they stop right there. This little area here that's gray, that's where the article stops right there. Now, they get the correct number, excuse me, for this fractional change in energy, but they don't really explain it very well. Whatever happened to clock speed? And what's the point of it? We know that there's a change in energy. There's a change in potential energy. There's a change in kinetic energy for a falling object. So there's a change in the energy of the frequency of the light. So this doesn't tell us anything. We want a clock speed, right? So what they don't tell you, they stop right there. And why? Because we proved relativity, but we didn't. You know, read the article for yourself. It's a lie. They take this equation and they give it a toss, and then they go back to the formula for potential energy. Okay, so oh, and by the way, this instantaneous change, this should be a delta. This here represents the change over the distance h. It's not an instantaneous change. And so they give you a, you know, kind of a hyped up differential equation, which is BS. But, you know, that's to further confuse and intimidate you. What they should say is that delta R, let's call that clock speed. R is the clock speed. So the change in clock speed divided by the initial clock speed, that would be the fractional change in clock speed, wouldn't it be, is equal to a negative GH over C squared. It's the same thing, except we use a negative here to show that the clock is slowing down. So these formulas down here that I wrote at the bottom here with R in them, that's it, the clock speed. And I simply substituted in the change in clock speed, fractional change in clock speed for this silly energy formula where they stop right there. And this obviously has nothing to do with relativity. It's a ripoff. This is just plain old Newton's potential energy formula. That's all that the experiment proved, except yes, of course, if the frequency changes as postulated by whoever, I mean, this isn't all that tough, then the change in clock speed changes with it. What's the definition of a meter? It's the number of wavelengths over a certain period of time, and that distance traveled equals a meter. So if the frequency is less, the clock speed is less, and the meter is less, all to the same degree, even though it's still a meter. No matter where you take this, even into a black hole, a meter is going to remain a meter. It's not going to shrink on the local level. But what we learned from the experiment here is that, well, let's look at it instead of, excuse me, instead of a falling object, let's think about what is happening to light. Okay, now, well, let me just explain here. If you want to tinker with these formulas, that's perfectly all right. I'll maybe try to explain what they actually mean. This is that your final rate of clock speed will be equal to your initial rate of clock speed minus the original change in clock speed times GH over C squared, or minus the fractional change in clock speed. So that will be your final clock speed, R1. And you can express this in different ways. Change in clock speed divided by original clock speed is equal to GH over C squared, negative. Or you could put it this way, and I like this one here. the change in clock speed is equal to the negativity of the original rate of clock speed times the change in velocity over c. So we get rid of those nasty squares. It's a change in velocity. It's the relative fractional change in velocity over the distance h. See, 9.8 meters per second, per second, per second. Okay, it's the change in velocity divided by the maximum velocity of light, c, which is equal to times the initial clock speed is equal to the change in clock speed. And so these things, you can just play with them till you begin to understand what they actually mean. But also understand that we could substitute R for L length, and it would be exactly the same, except that, well, it would be exactly the same formula. So length changes. It shrinks as you travel down towards the surface of the Earth because there's a change in velocity. Or if you shot a rocket ship at that velocity, okay, the same thing would happen. The clock speed would diminish. And the frequency of light would, well, it would increase. The wavelength would decrease. And by the definition of a meter, the meter would also have to shrink to the same degree. And this is going to be a question that pops up later on. If the shorter meter is still a meter, which it is, the properties of the smaller meter are exactly the same as the larger meter up here, but you never see that. All you ever see in your local level is a meter is a meter. So what's the difference between the solid inference that Einstein himself and the experiment reveals here and tells you here, it is a fact? What makes the longer meter different? Well, nothing. But obviously, one is longer and one is shorter. The farther you get away from the surface of the Earth, the larger the meter will get, or any other celestial body. So this difference between the smaller meters and the larger meters, as the meter grows, what makes up the difference? Nothing, but it's still larger. And that's the point that has to be made here. I didn't make this stuff up. This is Einsteinian physics. They're just not telling it the whole story, and they're not telling it right, because apparently he didn't really understand it that well himself. Okay, but this is well-known fact. The meter is going to be shorter. Closer you get to the Earth, the frequency is going to increase and the clock speed is going to decrease. So it's important to know that. And so I've got this, well, hang on for a second. Yeah, so I made up the summary of what we're looking at with the pound riptide experiment. The clock rate that the wiki article mentioned, of course, and we know that the frequency will change as well. And if those two things change, that the length of a meter will change. So the length of a meter and the passage of time will slow down to get over the change in velocity equal to the potential energy difference between 2 points, distance being h. Okay, so this is just Newton's potential energy formula. It has nothing to do with relativity or Einstein. And I don't know if these things were known before that time. This experiment was done in 1960, 5 years after Einstein died. So maybe someone substituted that article for him. You know, I don't know. Nobody ever knows where the stuff comes from, and the problems never show, you know, what the variables really stand for. They're not declared, which is necessary for problem solving. Okay, so this stuff is just all, this relativity stuff is garbage. Okay, but in this summary I just summarized those things. I explained them a little bit here. You can read it yourself. I'm not going to read it. When we get down here to the bottom, we see that over a distance h corresponding to a change in velocity, relative to the full velocity of the speed of light, okay, that fractional change in velocity or fractional change in potential energy is going to reduce the rate of clock speed by the same fraction. Okay, delta R, change in rate of clock speed, is equal to a negative original R times the change in velocity over the distance h divided by the speed of light. Now, if you understand this, see, that's what's really important. You have to be able to understand this and have faith in me that I'm not lying to you, and I didn't make this up. This is what the experiment says, okay? Please, give me that. Hang on as long as you can, okay? And also, of course, if the clock speed is less, the distance of a meter will be less by the same degree, and the frequency will increase by the same degree, or wavelength will decrease by the same degree, however you look at it. Okay, and the speed of light too. Notice this, that the fractional change is indicated by the Doppler shift, and this is Doppler shift. Falling objects, they actually do have a Doppler shift. So this isn't just gravitational redshift, it's Doppler in origin. Although if you don't have a falling body, you still have light as it leaves, it still undergoes that change in velocity. In other words, fractional change in velocity of objects falling in this direction is exactly equal to the change in velocity of light as it leaves the surface of the earth. That's what the experiment is telling you. That's what these equations are telling you. So you get this fixed in your head. But notice that everywhere you go, even though that meter, by this experiment, it's a fact that this meter is going to change in length, depending upon the concentration of mass in that area, the mass density in the given area. The more mass, the smaller the meter is going to get, and the less mass, the longer the meter is going to get. And yet it's still a meter. The properties of the meter haven't changed one bit. And because of that, wherever you take that meter inside the universe, inside the box, it's always going to measure the same. So how is it that the velocity of light is increasing? Well, why didn't you ask Einstein that question? Because this is a well-known fact of experiment that supposedly validated Einstein, that light, as it approaches an object of mass, it slows down and becomes blue shifted. Now, in departure, it accelerates and becomes red shifted. But see, the length of a meter doesn't change anywhere along that path. You can measure the change in velocity by experiment, by observation. You can see that light slows as it passes the sun and speeds up as it leaves. And you can also see the red shift. You can detect these things by various measurements, and they really don't say anything about relativity. You have been lied to. Just forget relativity and think about what is actually happening here, okay? If space is expanding, if a meter is growing, and you have a Doppler shift that says space is expanding, well, what does that mean? It means space is expanding. You just don't perceive it as expanding because inside the box dimensions are fixed, and that's why there could not have possibly been a Big Bang. All right, think about it. I'm not lying to you, okay? A lot of you out there call me a liar, at least, off that physics forum anyway, but okay, so I explain these things and you can see them, very plainly. And when you understand it that way, then and you're comfortable with it, then we can take the next step and we're going to look at a graph. Okay, let me dig that thing up here. I'll keep those thoughts in mind, but I want to take a little bit of a diversion here so that we can we'll explain how Einstein came up with his formula for the value of the deflection of starlight as it passes the sun, which we were talking about, the thing that got him the ticker tape parade in New York. His formula for that is 4gm over rc squared. Of course, g is Newton's gravitational constant, m the mass of the sun, r is the radius of the sun, and the speed of light squared. So 4gm over rc squared, and that's the full angle. But let me explain that it is understood that Newton came up, or not Newton directly perhaps, but that Newton's formula for the deflection of starlight would be 2gm over rc squared. And that's coming towards and passing. So Newton said it's gm over rc squared, and then gm over rc squared again as it passes. So it's 2, the full deflection of it, the full angle of deflection would be 4gm over rc squared. And you're probably not going to, these problems are going to just jump right out at you, perhaps. So I'm going to try to just help you along here a little bit. I don't know if this is really Newton's formula. It supposedly popped up first or approximately, I don't know, at some point 1805 in a paper by a guy by the name of Soldner, and Einstein was accused of plagiarizing that paper. I mean, this is a real common thing. You see this everywhere you go on the internet and you Google around. That formula doesn't occur in that paper. Not even that strange. It's just like, you're walking into a haunted house or something. It's kind of weird, but it's known as the Einsteinian solution. Gm over rc squared times 2 as it passes the sun. It's deflected by the force of gravity, is pulled towards gravity, and that was the assumption that Newton did make back in his day. And it's that light is a stream of corpuscles, and as having that mass, a very light mass or whatever, it is pulled like other objects. And he was in a big argument with a guy by the name of Huygens back then. Huygens won. Huygens said it isn't a stream of particles. It isn't a stream of corpuscles. Light is just a wave. It's a wave of energy. And Huygens won, and the argument popped for Newton's cork, or maybe it was just inhaling the mercury vapors from his alchemy experiments that made him daffy. But after that, but anyway, this argument, he was wrong. Okay, light has no mass, and that's obvious from the pound rupture experiment too. Now, didn't we just realize and verify and validate that light is not attracted by mass, but that it actually is pushed away at the same exact rate that bodies are falling in the opposite direction? That's what the experiment proves. You think about it, it's not, I'm not a crackpot, I'm not a cretin, or any of those other things these guys call me, but it's fact. So how could that formula be right? It's supposed to be a parabola, a parabola, that has like an infinite asymptote, and that angle of that asymptote would indicate the degree in which the incoming beam is deflected. But that isn't what light does. It moves the opposite way. Yeah, it moves the opposite way. Oh my. So how is it that Einstein claims that he rediscovered Newton's original formula, where there's no record of Newton ever having done such a thing? independently when it was based entirely on flawed assumptions. And Einstein, of all people, should have understood how light moved at that point in time, especially if at some point, he was, I mean, even after his death, he was credited for the Pound-Rebka prediction. Then he should have known that light is moving in the opposite direction. That's why he is a fraud. Another reason, an endless series of reasons, once you begin starting to really take a good hard look at this stuff, okay? So James Webb said there's no Big Bang, there's no Big Bang, and this is why. Well, let's talk about this just a little bit more. Why did then Einstein multiply the 2gm over RC squared, which should be the full angle, Newton's formula? Why did he measure it by 2 and come up with 4? That's a good point. You multiply wrong answer by 2, and it's supposed to be right answer. And why multiply by 2 anyway? But the idea is, well, you hear about it in 2 different ways. Since clock speed is slower, as we know from the Pound-Rebka experiment, that it would be further deflected. When you're going through glass or air, glass or gas, light is bent because it's slowed down by a transparent substance. The physical substance is slowed down and it's bent towards the normal. So if you look towards the sun as it comes up in the morning, it's actually 2 minutes ahead. What you're looking at is 2 minutes ahead of where it really is. And that's atmospheric deflection. It is a lensing, it's a bending, and it's also a deflection. It's the same thing. And that's a fact. Okay, we have that bending due to atmospheric. But anyway, the idea here is that the change in clock speed, is light going through glass. And so you double it. It's another gravitational effect. Well, another thing they might tell you is due to the degree of redshift. Think back on what we just did. Gravity is redshift and change in clock speed. That's exactly what it is. So why would you multiply it by 2? That doesn't make any sense, because it's all encapsulated. That is, you could describe it as change in clock speed. You could describe it as redshift. You could describe it as the force of a falling body. But it's all the same thing. There's no additives there. They don't multiply by each other. This is just one thing. So if you multiply it by 2, you're lying to somebody. You got some kind of underhanded reason, because it just doesn't work that way. But then here, Eddington on his little expedition measured, that it would be closer to 4gm over RC squared, and Einstein get his ticker tape parade. So he had to have known in advance. The paper had his gun cocked too, and Eddington, he was just waiting for this opportunity. And there's more of that, but I mean, come on, think about it, square up, and quit talking this little Einstein stuff. The Schwarzschild radius and the blah blah blah, and the twin paradox and the blah blah blah. Come on, guys. Get a real job, please. So anyway, we wanted to look at, okay, so shall we take a look at what actually is happening to light, how it isn't a parabola? And, by the way, geez, I forgot. If there's a 2-minute deflection of light in the Earth because of atmospheric refraction, then the atmosphere on the sun is far more dense than that on Earth. So you'll know that the majority of any deflection that you observe would be due to atmospheric refraction, and they forgot about that. So doubling it might not have been the best idea. You won't find anybody sign that. Oh, the sun has no atmosphere. Well, it doesn't work on the sun. Oh, it's just on. All right, they're a mob of crazy. So how is light? How is light deflected by the sun? Objects of mass, if at all. Well, we know that if this is the center of the sun, let's take a look at this graph right here. Okay, so let's study this chart here. And this just encapsulates what we've learned from the Pound-Rebka, what we've just gone through. Well, let's assume here that the center of this graph is at the center of the sun is at the center of the axes, the X and Y axes. And what we have here, the way I approach this, and the way it really is, it's just a vector problem. Einstein's equation is obviously wrong. There's no point in digging in that dirt any more than we have to, because it will just serve to confuse us. So what we want to do is we want to take the Pound-Rebka experiment here, and we just want to illustrate it graphically. Everything we said right here, okay? So here's the radius of the sun. The center of the sun is where the axes cross, 0, 0, and we know that in all directions, falling bodies fall at about 275 meters per second on the surface of the sun, and that is the Newton's G times the mass of the sun divided by the radius of the sun squared, which actually happens to be, radius doesn't have to be tangent to the surface. It doesn't have to be at the surface. It's just the value of G. It's the rate of falling bodies at the distance R. That's what it comes out to be. So at the radius of the sun, which would be little g for the sun, would be about 275 meters per second. That's how fast light is moving past the radius of the sun. And of course, it's accelerating at the rate of gm over r squared per second per second. Okay, so it's 270, it's the gm over r squared per second is the actual rate of falling bodies at the surface of the sun. And that is how light will be affected. It's accelerating away per second at that rate. And in the other direction, we have, if we have the velocity of falling bodies at this direction at r, light will have traveled in the 90-degree direction. In the direction of the y-axis, it will have traveled at the rate of c, or c per second. But we don't have to worry about per second or per second because it's all proportionally the same. You see, this is a simple vector problem. I think that I had this kind of thing about 50 years ago in my first calculus class. So I think in your calculus textbook, you should discover this, and you can see that I'm perfectly right. This isn't a difficult problem. It isn't a make-believe problem. We're representing reality here. And so a vector problem works like this. If there's a force, a horizontal force, 275 meters per second in this direction, and there's a vertical force at the rate of c, the speed of light, Or we could say the speed of light per second, if you wanted to think of it in terms of acceleration, because that's actually what's going on here. You see, well, light is being propagated by expansion. Oh, did I step too far? Okay, let's just go back and let's just think about this some. Okay, what we see here is the Doppler shift as light leaves the surface of the sun, and the rate of this. Well, let's go to an animated version of this. You see that light is moving away from the surface of the sun or any body of mass at an accelerating rate, but you don't see that inside. You can't measure that directly. Indirectly, you can measure it. A remote observer can measure it one way or another. But in the local sense, you don't, because all that's happening here is that the meter is stretching. See, it's real distance. It's a real deal, even though it's still the same meter. So everything inside your box appears to be fixed. There's no, things aren't expanding, but you see the evidence, the proof of the expansion in the degree of redshift as light is accelerating away from the surface of the earth. You see the waves are stretching out. So the meter is getting longer. But inside the box, you don't see that, but it really is getting longer. That's what I'm trying to tell you. This isn't a theory of mine. It isn't a theory. It isn't an idea. It's what the Pound-Rebke experiment and other experiments are actually telling you. And it's the same ideas pop up repeatedly in physics and cosmology. So, oh, look, we proved Einstein again. We proved Einstein again. It proves Einstein. LIGO works on, they'll tell you it's based on Einstein's idea of length contraction, because when the gravity pulse comes, when the gravity wave comes zipping through, it'll shorten the arm of the LIGO experiment, and you'll get a deflected line of sight with a ray of light, and so you've measured a gravitational wave. But it's a lie. Well, I mean, it's half a lie, isn't it? Because yeah, the length is changing, but not locally. You can't measure it change. Why? Because the clock speed shrinks along with it. That's how gravity and space work together. Forget about these fishnets and steel balls. Clear your head. You might lose your job. Okay, so what? Anyway, okay, so you can see that this rate of expansion is exactly equal to the rate that bodies will fall in the opposite direction. And you'll see that if light is traveling a distance, the radius of the sun in this direction, and is traveling at the value of the rate of falling bodies, or the rate of expansion of light away from at the surface of the sun, and there's a matching figure, on the y-axis, and where that crosses the y-axis, that's your angle of deflection, theta. And you will see that the assumption here is that the origin of this light, there is no mass. Because if there was any mass, it would be pushing on the top as well as the bottom. And of course, if you're looking at light coming from a distant object, no matter how distant, it is exactly the same mass as the sun, it won't be deflected. These lines will be parallel. So the graph embodies what the Pound-Rebke experiment is telling you. Light accelerates away from the surface of the earth, and we see that manifested as redshift. We don't see it directly, although we might measure the change in distance, by other methods. And that has been done in other experiments. So this is my idea. This is my theory. It's a fact. And it comes out to be, in this case, where there's no mass on the other end, it comes out to be 0.189, 1882189 to 3 significant digits, 189 arc seconds. Way smaller than Einstein's figure. And not only that, but I was just shooting from the hip, and out of habit, I said, well, then the total must be double that. And I go, oh, wait, I'm thinking about it. Well, wait a minute. No, this is a linear. Okay, it's not tangent at this point. It's going to connect with the sun here at this point, and that tangent to the sun. That's the only place, by the way, that any other waves coming through will miss the surface of the sun. So this is our angle of deflection. There's no way around it. I don't know. Get out your calculator, and I'll show you how the problem goes later on. I'll solve the problem. Get out your calculator and check me. Is it 0.18882? I think so. But that's what it is. But of course, if the mass of the object from which the beam originated, if it has any mass, the angle is going to increase. It's actually going to, let's call this a negative, because it's going the opposite way of what we need for an angle of deflection that will give us gravitational lensing. It's going the opposite ways of what Einstein said or what Newton might have said. But if the mass from which it's coming, if the mass density in that area is equal to the sun, there won't be any angle of deflection at all. And if it's twice as much as the sun, then I suppose it would be a positive 0.189. All right. So then that would contribute to whatever deflection is due to atmospheric refraction, because the sun certainly has quite an atmosphere, which nobody can deny. So I don't know how Einstein and Eddington got this. Some guys, life is tough, isn't it? So this will give you your actual angle. If you're not familiar with vector math, it just works like this. You got a force going this way, and you've got a force going this way, and it turns out to be that the net force is this. Well, it's the hypotenuse of a right triangle in this case. I don't think it has to be a right triangle, but anyway, this is a simple, really simple. This is the simplest vector problem you can really have. And what you've got, a vector has magnitude and direction. So W here, which is the force of expansion, or we could just say the velocity of light going in that direction, which is equal to c over s. And of course, we have to add a little bit because it's getting a little bit of a boost from the sun too. Not much relative to c, but I mean, we're going to be accurate. We want to figure that in there. So the magnitude of vector W is c over s plus gm over r squared. And it's acceleration of, well, come on, think about this. Come on, you guys are scientists. If the space around the sun, well, in the sun itself, well, we just don't see that, is expanding at 275 meters per second, then the universe as a whole is expanding at the speed of light. The potential energy of the surface of the universe is mc squared. Well, let's not go there just now, but that's actually if the universe as a whole is accelerating, and that's exactly what's happening down here to light as it leaves the Earth, then that means the potential energy at the surface of the universe is, and that also means if the universe is expanding, it also means that we're fixed in relation to the motion of light. So the speed of light, if the speed of light increases due to, as it leaves the surface of the sun, it's going at 275 meters per second, then it'll be leaving the surface of the universe. The universe will be expanding, actually. It's not leaving, it's being propagated by light, is propagated by the expansion. And because we're fixed inside, we see the transmission of light only. That's the speed of light. See, it's the rate of expansion of the universe as a whole. And of course, as it continues to expand, the value of C continues to increase, but it's all the same to us inside. The dimensions are fixed, the speed of light is fixed. The universe has a radius r, it has a mass m, and it has a rate of acceleration fixed at c, the speed of light per second, which we perceive of inside the box as just the speed of light c, just as we see bodies falling at radius r at 275 meters per second. It's simple, routine, basic, rational inference. It's not even inference. It's just, this is what the Power-Rocket experiment is telling us. And you could trace back through this, over and over. If you know anything about, if you're familiar with vector math, you'll see that this is perfectly all right. The resultant vector is called the sum of u, which is horizontal, and w, which is vertical. And you can calculate that as the hypotenuse of a right triangle, and you can come up with the vector v, which actually represents the, the velocity of light of the resultant. We don't really care about that too much. We just want to figure out what it is so we can find this angle of deflection. And so the vector v will be equal to u plus w, which is actually the hypotenuse of a right triangle. You can figure out that for yourself. And then you use the law of cosines to figure out what theta is. It's an easy problem. But you'll notice that light is not curved. It isn't attracted to by gravity. It isn't curved by gravity. It's deflected. But the deflection is linear throughout and one directional. I know it's going to probably be impossible for you to accept that. Go back over and over and over until you realize, where I'm wrong. And I'm not wrong. This is right. So, I suppose maybe we should take a look at solving this problem, and that brings up another issue: is solving problems in method science. How do you do that? Okay, just give me a second. I need a drink. I'm getting old, and I'm old and tired. Okay, when you set up a math or science problem, and I've done thousands of them, generally you put your knowns up at the top. Well, and along with any equations, you want to put down any equations that you need to solve the problem and identify what those variables in those equations are. And then you want to calculate what those values are. And you want to solve for the unknown. So our unknown here is the, well, the magnitude of V first, so that we can find what the cosine is, and then find out what the matching angle is of deflection, theta. So first we calculate the absolute value of the vector u, which we know is going to be equal to the mass of the sun times Newton's g divided by r squared, which is the rate of falling bodies at the distance r on the surface of the sun. And that's not too tough, but notice this is a tiny, tiny angle, so you're going to have to run your digits out there quite a ways. I don't know how they did this 100 years ago, or 2 or 3 or 400. I mean, my gosh, think of the wear on your pencil. And then the vector in the vertical direction is simply the speed of light, or if we're going by acceleration, we have to put a second in there, but we're not going to actually need that. So it's just mg over r squared as before, because that's, where we're getting this additional boost to the value of c, and it's that plus c over s. We calculate what that is, and again, you better carry a lot of digits, fistful of digits. And so the formula for calculating the hypotenuse of that, of w and u, is equal to the square root of, now this is as complicated as it has to be, but it's as simple as it can be. This is the way you do it. You don't do math like Einstein and all this little devils do. They get all complicated and they don't declare anything. Here, you see what everything is declared. Well, I don't declare M and G outright on the paper because we know what those things are. All right, everybody knows that. So I'm not talking over your head, hopefully. So it's the square root of w squared plus u squared. So combine these two expressions, square them, take the square root, and that's what you get. That's the vector u. And from that, we can calculate the cosine of theta. And the cosine, using the law of cosines, the law of cosines is that it's equal to w squared plus absolute value of e squared minus u squared over 2 times vw. Any absolute values of. And you see you get a extremely small number. The cosine is equal to 0.99999999999. To get that right, 581. So the most you can get out of this is 3 significant digits. I suppose I could have carried it a little farther, but what's the point? And so you can look up the arc arc cosine, the angle whose sine is 0.999. Now, maybe I did this wrong. I don't think so. You can check it out yourself. You just Google it and get an online converter, and it comes out to a negative. I say negative, just going the other way of Einstein, maybe Newton, negative 0.18882 or 0.189, 3 significant digits. Okay. That's all there is to it, But Eddington's observation was 1.75. Of course, that's both sides. And of course, an assumption they made, which is wrong. But if you take the total of 1.75 to the extent that he was correct, and subtract a negative 0.189, because that means you're going to have to get more of an atmospheric refraction to make up for that over and again that. So that gives you 0.975 of an angle on departure and an angle on approach of 0.785 arc seconds. And now, listen, I'm not immune from making mistakes. Don't get me wrong. As a matter of fact, the only reason I'm good at solving these problems and making a lot more progress than most people can do, even at age 74, is simply that I put a lot of time and effort into it. And just check me out, but I do make mistakes, and when I was going through school, I had an A at the end of the class, and I was probably the top grade in the class, but not necessarily, because I did have a tendency to make mistakes. I have Lyme disease, and it just wreaks havoc with your concentration. So I have to fight with that all the time to stay focused. And every once in a while, I drift off and I make a mistake. So you check me out and see if I'm right. But the way I'm doing it is right. So please don't fault me on that. Well, maybe you see something I don't. I'm happy to hear that. But I'm reluctant to open any emails or take any phone calls because most of them tend to be a very unpleasant experience. But if you can approach me right, okay, there we are. One more break. There's one more thing I want to touch on before we finish up. Thank you. Yeah, I did this nut and bolt on Photoshop. Pretty cool, huh? All right, so let's summarize on this page here. A numerical solution to starlight deflection by the sun. We're just going to summarize that. We got the absolute value of the vector u, which is the horizontal rate of expansion or rate of falling bodies at the surface of the sun. And we got the absolute, we calculate that, mg over r squared equals boop. And we've got the absolute value of w, that's the vertical, which is essentially the speed of light. And the resultant, or sum of those two vectors, b. And we calculate those things, and then we have a numerator and a denominator to give us the cosine. And then we can find theta at 0.189 arc seconds and summarize these figures. And that's the end of it. There's one little thing I wanted to cover, and that is why did I forecast that the James Webb Telescope would disprove a Big Bang, which it did. There, if you notice, there's kind of a chill out there. There's not so many videos coming out about the Big Bang, and all this. It's 49 billion years wide, and because it was expanding over this period of time. See, what they have done, these idiots, is Einstein and Hubble got together and they realized that there's a progressive redshift looking back farther and farther in time. And you can correlate that with what they call standard candles. You can correlate that with distance. So you've got, so many billions of light years going this direction. And there's a redshift associated with that. And you find that same relationship going no matter how far you look back. That's progressive redshift, and because it correlates with distance, they say that the planets and celestial bodies are moving apart. How foolish could they be? Honestly, because we see this gravitational redshift, but nothing is moving apart. Well, it's not moving apart as we perceive it, but into an external infinite void, yes, everything is moving together apart, and you see this redshift, but the raisins aren't moving apart in the Earth. And so what are we actually looking at here anyway? And why is this, this is a progressive redshift as you're leaving the Earth. You know that the universe as a whole is accelerating at c per second. And c changes by the value, addition. It's a geometric progression. In other words, the Big Bang is happening now, and it has always happened. And that force of expansion is what is necessary to sustain the force of gravity. Mark my word, I didn't slip something in here. I'm telling it to you straight. Okay, so if we look back farther and farther in time, what do we see? We see a smaller universe that actually is expanding at a much smaller rate relative to the difference in size between us and them, because as we expand at a progressively greater rate. So there's going to be a progressively greater redshift between now and way back then. You see, it's a progressive redshift. But inside the box, within the radius of the universe, which is fixed by our measurement, expansion into an infinite void does not affect the properties of the matter within. See, this is a different level of space. This is the real void, and it really is out there as much as any of these observations that supposedly proved Einstein, this is what they're telling you, okay? And I don't know why they didn't get it right. I don't know. There's a certain amount of dishonesty. There's a lot of dishonesty there. And I know there's a lot of crackpots that have come up with ideas that are supposed to challenge Einstein, but this is a solution to a problem. Geometric, illogical. This is correct. That's what it's telling you. It's not just wild inference, it's how math and science, math and physics work together, math and reality. You can describe reality in terms of that, but they're not free creations of the human mind like Einstein said. That's baloney. That's Einstein. That's relativity. Baloney. The mathematical relationship that exists is not a free creation of the human mind. It's a recognition. It's the way that reality is speaking to you. It is either correct or it is incorrect. And it's not up to you. It's not your free creation. It is your obligation to discover it and describe it accurately, which is what we've done here. So, I guess that about does it. Thanks for listening to me, and I hope you benefit from what I had to tell you, because I think this is probably the only place you'll ever find the truth. If you can understand the truth, then I don't have to convince you. If I have to convince you, and it's all that hard, just forget it. Just go away. But there's somebody out there like Louis Essen who said that about Einstein's formulas. They don't really mean anything. It's just a joke or a swindle, was the book he wrote. Is it a joke? Well, I think it's more of a swindle than a joke. But here you get the real deal. And thank you for listening. And I'm going to let you go for the night. Thank you very much. Bye-bye.